for inviting me here today. As Deborah mentioned, we are one of several consultants that supported PIVC and Engineers Canada in their study, which is what I'll be speaking to today. So I'll be speaking about work done by others as well, and we have one piece of it, which is the Quesnel Bridge, which will be in here. The study was carried out, as I said, by Engineers Canada, PIVC in partnership with NRCan, as well as with the owners of the infrastructure study. So first of all, what do engineers do? Oh, back now, let's see. What do engineers do? Well, we plan and design infrastructure. We support, in order to support current and projected needs. We consider many aspects, loads, of course, serviceability, over the lifespan, capacity, safety, the loads, there's gravity loads, there's seismic loads, traffic loads, environmental factors. And so climate effects are only one of many in combination with others. And climate effects are considered and have always been in the design of infrastructure. So in order to carry out this design, we do have tools we use, which are based on underlying science, but really we're looking for a practical application of the underlying science. And we do this by using codes, standards, guidelines, as well as professional judgment. And it's also very site and structure specific. Life cycle considerations are important. The design life of infrastructure can vary from a couple of decades to 100 years. And we also need to take a holistic approach in doing this design. But really, engineers need practical solutions that can be applied while there's still many unknowns. So it's really a risk assessment, a risk management process. What does climate change mean to engineers? Well, we acknowledge it's a reality regardless of the cause, and as Eva said, that really isn't the point in what we're discussing here either, but we are seeing changes. Engineering profession does lag scientific research. It's the application of science necessarily rather lags it. We realize somehow we need to accommodate it, but we don't really have strategies yet to do that on a day-to-day basis. The potential consequences we can immediately see, premature weather and deterioration, which affects the design life and the lifespan of the infrastructure, which leads, of course, to higher maintenance and operation costs, replacement costs, and reduced performance over reduced life cycles. So we do have a responsibility to find ways to assess the situation and do this risk management that takes into account potential climate change, and to develop policy standards or guidelines in order to do so. And as Eva also and the previous speakers both mentioned, that it is very much a multidisciplinary and a multi-jurisdictional approach is necessary. So mitigation and adaptation, the two parts of it, then here mitigation engineers have already been working in this area. We know about that. Adaptation is still rather emerging, and we really do need greater understanding and more tools. The first National Engineering Vulnerability Assessment of Public Infrastructure. So this is sponsored by Engineers Canada, which is the organization in Canada that represents the profession of engineering. It develops standards of practice and promotes engineering and continual sort of education of engineers in Canada. Engineers Canada created PIVC, which is the Public Infrastructure Engineering Vulnerability Committee, and it was established to look at this issue of adaptation and the vulnerability of infrastructure to climate change impacts, in looking at the adaptive capacity, potential vulnerabilities, and involved multiple levels of government and consultants. The study took place over the last couple of years and was concluded just now in June this year, and the results are posted at their website, which I'll provide later. And there's a next phase that'll be starting up soon for the next 2 or 3 years. And the purpose of the committee is to assess the vulnerability of the public infrastructure to potential climate change. Just not to look at this in detail, but just as the process that's being carried out until now, the PIVC approached the topic of adaptation by creating 4 expert working groups, one for buildings, one for roads and associated infrastructure, which includes bridges, culverts, etc., one for stormwater and wastewater systems, and one for water resources. So they developed a protocol to use to have in a consistent way to tackle this problem, which I'll describe in a bit of detail. And as a result of this was a report that I mentioned was issued just now in June for infrastructure in each of these 4 categories. What we really want to do is look at the interaction between climate and infrastructure, and we need a way to assess the vulnerability and we need to consider both the infrastructure, which is represented by the white circle on the right-hand side. And engineers, they pretty much understand this. We know about the structure of the infrastructure, or we can find out, we can test, we have information, we pretty much understand that. But on the left-hand side, the climate effects, the climate elements that could impact the infrastructure, this is where, this is going to be new for us. We rely on our codes to give us design parameters, but now we need to look at this in a more broader way. And we need to look at the historic and extreme climate information we have, as well as climate change scenarios. For the purposes of the study, engineering vulnerability climate change is the level of risk of destruction, disruption, or deterioration of engineered public infrastructure resulting from changes in climate conditions. And so it's not necessarily the destruction or catastrophic destruction, although there is that element, but also just over the long term, the increased rate of deterioration, which is also something we need to worry about. So PIVC developed a protocol, which is a mechanism developed to have sort of a stepwise approach to assessing the infrastructure. Steps 1 and 2 essentially define the project, that define the infrastructure itself, which is relatively straightforward. It also needs to define the climate impacts. And this was a combination of historical local information, very site-specific, as well as projected climate effects due to climate change. Step 3 is really the main step in this process, the vulnerability assessment. And here it was very much a multidisciplinary approach. When we were ready to do the actual assessment or the screening of the effects, we involved people from various parts of the organizations that sponsored the study. So for instance, for the Quesnel Bridge in Edmonton, we tried to get together people from the planning departments, engineers, operators of the maintenance departments, and so on, to have as comprehensive and as cross-disciplinary view at this as possible. And indicator analysis, where we need to fine-tune or refine some aspects, and then of course some recommendations, which I'll hit some of those in this presentation. So as part of the PIVC study, 7 case studies were conducted across the country, so a variety of geographies and climatic areas, as well as a variety of infrastructure. So in Vancouver, looking at the sewerage area in Greater Vancouver, the Quesnel Bridge in Edmonton, water treatment facility in Manitoba and Portage la Prairie, Sudbury again, which is interesting. We'll be speaking about that as well, for the roads and other infrastructure, buildings in Ottawa, and then out in Placentia, the water resources and various structures out there. And then a kind of a unique situation up north, Thermosiphon. It's interesting because it's relating to the permafrost. It's one of the critical areas in Canada. Climate factors. There are several relevant climate factors we need to consider. These first 4 bullets are very sort of typical parameters that we're used to seeing, referencing our building codes for: temperature, rainfall, snow, freeze-thaw cycles, the peaks and the averages. And these lend themselves to climate change forecasting. Projections are not so certain for extreme events, which can be, of course, of greater interest, but difficult to project or predict. Wind, ice, snow, hydrological effects. How do rivers behave? How does river ice behavior change with climate change? And then, even more complicated, the combination of sequencing of events, water, heavy rainfalls following snow and ice buildup, etc. The climate change scenarios that we used here, the information was obtained from Moreno's consortium in Quebec that provided what they did was they used the downscaled the global Canadian model to read quite a fine regional model, a 45-kilometer grid, and that gave us predictions for all our basic climatic parameters, rainfall, snow, etc. What they were able to provide for us was adequate for the screening level that we were doing, looking at 3 30-year time horizons, which do capture the life cycles that we were interested in for the infrastructure. Now, the quality of the data varies because, of course, it's based on historical information, weather stations, and so on. So the quality varied a bit, but for the screening level, we found it was adequate. Of course, where it gets more complicated but more important as well, the extreme weather events in Canada impact our infrastructures, as we can see here and as we heard about already. So for each study, we tried to look and obtain very local information. So for Edmonton, for example, the historical events are well known by engineers. Engineers in Edmonton know that they're going to design for the 1915 flood, which is the high water level in Edmonton. But these can really determine how engineers and local practitioners operate in that region. So it's very important to capture the local knowledge and experience, which is why you need to work closely with the owners of the infrastructure. So the first study in Portage-la-Prairie, the drinking water treatment facility, the Assiniboine River is subject to variations in flow and turbidity and vulnerable to flood, to drought as well. So all the components of the system, mechanical systems, the intake and outflow, were all considered in the study. What they found was nothing was significantly vulnerable to climate change impacts. One of the key areas for consideration, though, was on the operations side. So if there were extreme events occurred where the operators themselves cannot get to the facility, how can the municipalities manage this situation? So it's really more around emergency preparedness. And that is often a theme that came up repeatedly for all the studies, is more about the operations and the preparedness side of things. And then the other thing they recommended was going forward, planning, as the natural cycles of planning came around for the facility, to take into account climate change effects. And that also was a recurring theme going forward. Placentia in Newfoundland, 4 different components were looked at: breakwater, backside wall, all to protect the town. Town hall is in the flood plain, so that was considered a higher risk infrastructure, and then the main highway. Now, in 2007, Placentia had seen the effects of a tropical storm Chantal, and at that time had seen some pretty catastrophic events, and bridges were washed out, roads were washed out, etc. So they had a very real sense that they needed to be looking at this more carefully. The increase, of course, in rainfall capacity, but intensity, but superimposed on, as was mentioned previously, sort of a rise in sea level. So the combination of a rise in sea level and storm surges, sort of overcoming the systems that are in place. Some of the recommendations that came out of this particularly was establishing a land use plan that can minimize stormwater runoff, to improve monitoring of flood protection structures and account for the rise in the floodplain groundwater in the region, and to take into account in planning not to have buildings in the floodplain, of course, for instance. Sudbury, the roads and other structures such as culverts, as Emma mentioned as well, it is a very large municipal area, 3,500 kilometers of roads in a 3,600 square kilometer area. And many lakes within the city boundaries. What they found actually in Sudbury that was highlighted particularly because of both the rise in temperature and the prolonged periods of high temperature, where there was a concern around the durability of the pavement or softening of the pavement, and therefore increased rutting and decreased in performance over a decreased life cycle as well. And more research was identified that should be done in that area, the paving materials and so on. And maybe they need to look at different paving design mixes in the region. More rain on snow events, more combination events, and higher rainfalls, and that can impact the culverts and other drainage systems. So that, as they go forward, we need to look at, take into account any increases in temperature or in rainfall. The Quesnel Bridge in Edmonton was designed, it is currently a 6-lane bridge over the North Saskatchewan River just west of Edmonton, and it's currently undergoing rehabilitation to provide 2 additional lanes, and that's just to increase traffic over the last couple of decades. But it did provide an opportunity to look at this, to take into account any potential climate change impacts on the existing structure. What we found, in fact, is, again, it's the higher rainfall, the higher intensity that could have an impact on the drainage system, and that's the only component of the bridge that showed some potential vulnerability. What indeed happens, though, is when it comes down to designing in bridges, the critical design elements are the larger forces on the bridge. So for the drainage system, it's easy enough to accommodate within the